Hey guys, my name is Josiah Clark. I'm the Chief AI Architect over here at Liqid. Fundamentally what we do, just kind of super high level, we have a composable computing technology that enables you to disaggregate devices like SSDs or GPUs from the server so that instead of kind of being limited to what's inside the box in your typical server, you can basically scale the devices to your needs. So what I do for the company is primarily focus on taking that technology and applying it to AI, really machine learning, deep learning, and basically identifying ways we can really help that market. So I'm just going to dive right into this thing. So as a company, so like, okay, why is this hardware company here talking about AI? Liqid's like a hardware company, right? And that's true. We're not cranking out algorithms and doing all that fun stuff. But as you know, if you spend any time building machine learning algorithms, you'll relatively quickly realize that hardware is one of the primary bottlenecks in performance and the amount of time it takes to improve your algorithms and kind of do what you want. So we all know it's a pretty data and compute intensive environment and application. And as an infrastructure company that can kind of right size things to exactly what customers need, or folks who are actually applying this stuff in the field, that's really where we come in. So what fundamentally we do is we're solving the infrastructure challenges, or some of the infrastructure challenges that folks who are applying machine learning, deep learning in the field are running into. So there's, as a hardware company, a lot of people start in the cloud, and that's a great place to start. But usually organizations kind of go through this metamorphosis where they'll begin testing ideas and playing around on cloud platforms, or even building prototypes, and some companies actually are building products there. But there's kind of this cost calculation that we're all aware of, where actually taking your equipment on-prem once you reach a certain size, usually will save you between like 11 and 20x, and sometimes more if it's done right. So when individuals or companies are beginning to look at this a move to on-prem, or maybe they have a requirement based on their data sets to place their gear on-prem, what usually people are going to find, and if you just look at like what's available on the market, there's limited configs available. Servers come out usually like a server that will support a GPU, unless you're going with like a DGX A100 or a DGX model or something like that. Usually those will come out, several months after, the latest and greatest GPU is released. And then you don't really have much control of them. You basically either get like the 500-pound gorilla, or you get, some server that's, can only have 4 or 2 GPUs in it or something like that. You're kind of at one, or you're at the DGX side of the spectrum, or you're at a 2 or 4 GPU node server or GPU server. And then there's always the fun part after you've been spending all your time doing all that fun math and wrangling all your data in the cloud, and suddenly someone's like, hey, we need to move to on-prem because we're gonna save a bunch of money. Fundamentally, with the training side of deep learning at scale, is definitely an HPC type problem. It's not HPC specifically, but the type of equipment that you're going to be using, the power, cooling constraints are all kind of very similar. So most people who are really good on the algorithm side, the data side, don't have a lot of experience in that area. So hopefully we can help. So it sounds like a lot of that you folks are familiar with the field. I always kind of go over this because it's relatively important to not forget about this. So there's this thing that we call the data flywheel, or the virtuous cycle of AI. And basically the way it works is machine learning based applications are kind of like they have an economy of scale associated with them, similar to how Google kind of took over search. So the way the wheel works is you basically release your application, you start collecting users' data, more people start using your data, you get more data, you can train more training, more data equals better models, better performance equals more users. And that's kind of what we all saw, with Google back in the day. And that's what helped them actually kind of take over the web search market. And that same concept applies. And as a company who's looking to do this on-prem, or even if you're in the cloud, doesn't really matter. The whole goal is to move around this data flywheel as quickly as possible. So you kind of be the winner in the winner-take-all market that AI kind of is. Most statistical learning applications kind of end up working out like that. So the goal is move around this data flywheel quickly. So as you make cycles around the data flywheel, if you're successful, what's going to happen as your model performance increases, you're going to start to see an exponential curve start heading north for data and compute costs. The model's still going to be performing better, but your costs are going to start going up. So having the ability to flexibly scale that, and also just kind of having this as a—
Hey Josh, is that because of model complexity increasing, as well as the data size or number of data items increasing?
So,
I mean, is it both of those, or is it just data?
So it's both, actually. I mean, so like typically you're not going to like start off with you're not with the same model you started with. You're going to have a specific use case, a specific task that you're trying to train a model to perform, or maybe you're going to have a specific area of focus, like insurance or autonomous vehicles. Yeah, exactly. Yeah. So you start off with usually what people do is they'll start off like a baseline model. Back in the day, everybody was from like object detection would do like ResNet or something like that, and then they moved to something like Mask RCNN, which is like a semantic segmentation model. The data sizes are larger, so the amount of really like the size of the image is actually larger. So to process like same number of or connect the same number of semantic segmentation, training runs as object detection, you're going to end up pushing a larger frame. So like your data. So just from a model perspective, like ignoring all data, like pretending your data never changed, what's going to happen is you're going to want to. Most people do is they end up moving to larger and larger actual individual training examples. And then also there's this thing we call the scaling hypothesis. Is like GPT-3 and kind of everything out there is always reproving this, which is basically the more data you have, better your model performance, but then also the size of your neural network that you're training, the better your model performance will be. And I guess GPT-3 was probably the big thing, when everybody's talking about that, oh my God, like the computer's alive or whatever. All they really did going from like GPT-2 to GPT-3 was just like making the model much larger. And that drives up your compute costs.
So it's both more precise data, more precision in the data, driving that compute cost, but then the model itself increases in complexity.
Yeah,
and nodes and such like that. Yeah,
and you don't have to, So like, if you're in some market or have some task that you're trying to train a neural network to perform, and it does wonderfully and totally helps you dominate your market, then there's no reason to go make it any better. But typically, there's this kind of continuous improvement process, and then also a lot of companies will start with something simple, and then they'll start adding more complex models to kind of build out capabilities around like the primary use case. But with all of that, you end up with more data and more compute requirements.
Got it.
Yep.
All right. Thanks.
Yep.
A quick question. This Andy.
Hey, go ahead.
That's the same problem that HPC is trying to solve, right? Amazon, Azure, Google, Rescale. There are a bunch of companies trying to solve the same problem: composable infrastructure, high performance architecture for the AI.
Yep.
Okay, so pretty similar.
Yeah, fundamentally, I think all of us are trying to provide where a lot of the work we do is with OEMs like Dell, and everyone's kind of trying to do the same thing right now, which is okay, how do we build better systems, really hardware platforms to support AI. And they definitely are very similar to kind of what everybody's doing is they're using the HPC, what we had on the shelf for HPC. Even like NVIDIA, they're one of the reasons they're able to pivot so quickly into the AI space outside the fact that, GPUs are great for vector operations and linear algebra calculations, is that they were just kind of positioned, from that, HPC world to just be like, oh, this is similar. We've got a tool that solves that. So what everybody's really trying to do, I think what I see is everyone's trying to like right size that. Well, it depends on the company. So some companies are trying to like right size AI, and where on the opposite side of the spectrum, you kind of have NVIDIA. It's like, hey, we're going to give you the 500-pound gorilla. It might be more than you need for some things. So you might be, you might, basically be paying for power for all the NVLink and stuff like that. You might not be able to use it. We don't care. Here's the full. Here's one big system and one big building block. And then you have other companies that are trying to look at, what they currently have on the shelf. They're different server platforms, and they're trying to determine, okay, how do we, which systems do we kind of upgrade for, a better, a more diversified like training. Really, it's training and inference too. That's
I get that. So it's basically that's what it is, right? I mean, when you have to do a particularly medical imaging model analysis, live analysis, you need a ton of horsepower that you can either provide that, or if it's a smaller one, I'll just right size it to what you need. I get that from the model creation perspective. One of the problems that I always have with the HPC is they are in the model creation space, not as much in the model inference. In other words, when you move the models to the field, you're on your own. So are you guys doing something on that front? I'm curious about that.
Yeah, we actually are. So, and not for all use cases, because there's models on your iPhone and stuff like that run just fine.
Right.
And then, self-driving cars and stuff like that, you probably don't want like enterprise equipment sitting in the back of, every Tesla. But for a lot of the kind of enterprise at the edge type stuff, so like supermarkets trying to restock shelves and, monitor customer interactions in a store.
Or oil rigs trying to crunch everything within the rig.
Absolutely.
Letting the data out. Okay.
Absolutely. Yeah. So actually kind of there's all these different weird problems you run into at the edge. So one is like telecom cabinets are the standard. Well, you can't stick a DGX in a telecom cabinet. You also run into every I would say like although there is a lot of diversity from a compute and storage perspective on the training side of the house, there's even more diversity from a deployment perspective. We actually deploy, your inference and application. So for the use cases where, it's kind of that enterprise at the edge, usually they'd want a server.
Yeah.
We actually can help a lot there. And that's really just kind of from the right sizing perspective, where we can, we kind of have an unlimited amount of options for you to, basically compose the right server that you need. Although there is a lot of, hyper-converged infrastructure and virtualization stuff out there, the problem that people have always run into with that is the performance penalty, right? Or even like virtualization, you can only pass through a certain number of devices. Whereas with what we've done, we've basically kind of taken that hypervisor approach, that allowed you to utilize more of the compute and memory resources available in your server that might not have been being utilized. But what we've done is we've gone upside down and done that for basically IO devices. So like GPUs, SSDs, and for the most part with AI, it's GPUs and 200 gig NICs, 100 gig NICs, different types of HCAs to feed the data in, whether it's coming from a bunch of cameras in a store or that's coming from a large shared storage, parallel file system that you're using for training models on. So those are kind of the two really primary
I want to follow up, not now, but maybe at a later time, because the other thing I also seen you touched upon now, you don't have to necessarily do all of the model trainings on the cloud, on the HPC cloud. If it's a smaller model, just incremental adjustment, you could even do it at the edge, as you were talking about, because the enterprise extends to the edge, right? So that's another thing I want to talk about. I don't want to hold you, but that's another topic that's very fascinating to me. So maybe we can take it offline and talk.
Yeah, absolutely. Love to go into that, and I can kind of share with you what we're seeing, in kind of like the federated learning space is what everybody's calling it right now. Yeah. So you actually, this is kind of we just covered this a little bit. Basically, when you deploy to the cloud, one of the really nice things about it is it's flexible. You can scale it up, scale it down. You can right size it. If you get it wrong, you can turn it off. Whereas on-prem, you're kind of stuck with these, certain shapes of compute and storage and network interconnects, and there's a ton of nuances that actually go into, optimizing the bus architecture and really it's the bus architecture primarily, and the communication, the physical layer of communication between all these devices, to make an efficient deep learning platform. And that's whether it's for inferencing, where you have a ton of data coming into the thing, or whether it's for training, where you have data coming in batches, but you need, tons of GPU horsepower, kind of as much GPU horsepower as you can get for the most part. And then you need to balance out the HCAs. But the problem is, that people are seeing today, and you guys kind of alluded to, like, companies are trying to figure out, okay, what's the next killer AI system? And they're all building these different boxes, but they're all still, there's just not enough in the market right now to meet all the different use cases. So, you end up either with something that's bigger than you need, or it's too small. And then usually people just go and buy DGXs and say, screw it. But that's kind of, the world today, before we came around. I'm not gonna really spend too much time on this one, because it just kind of talks about, what I alluded to earlier about virtualization. Over the past, 20 or 30 years, we've basically, all of our disaggregation has happened at the software layer. So you always have a physical box, and you can virtualize on top of that physical box, but you're limited to the amount of resources that the box can contain. Containers help a little bit with that. They're more efficient, so you can actually pack more stuff in there, but you're still just limited, to what the box can contain. And then there's the on-prem infrastructure as a service model, where you have somebody else worry about it for you. But even those organizations are still, they're limited to the box, and nothing's wrong with any of these approaches. We actually work with a lot of these companies and help them do all these things. We just kind of do it a little bit differently.